on three different things. One is functional neuromuscular stimulation to evoke movements in paralyzed limbs. Basically, what you do is you have some kind of an electrode implant in the peripheral nerves. You apply electrical stimulus in such a way that you get the movements you want. Then we talk about intuitive control of prosthesis. What we mean by that is you think about it and the movements should happen. Again, the whole idea is when you think about it, there are electrical signals that will happen, bioelectrical signals that will occur. You record those things using sensors and use the sensor signals to interpret movements. Okay, in fact, I would explicitly state that part. And then we want, of course, to interpret or decode human movement from these bioelectrical signals. The bioelectrical signals can be multiple, can actually come from many different sources. The most common source that we use for amputees and prosthetics, artificial limbs for amputees is electromyograms or EMG, which you can actually obtain from the skin. You can also obtain EMG from the muscles, but you have to implant an electrode into the muscles to make that happen. You can get signals from the brain, for example, electroencephalogram, EEG, basically is brain signals that you collect from outside, in the sense it's non-invasive. You can collect signals in an invasive manner from the brain. ECOG or electrocorticograph is something where the electrodes are just outside, just under the cranium. All right. Or you can go deep into the brain and actually implant electrodes there and collect signals from parts of the brain that actually is involved in the movement decisions and things like that. Okay. So what I want to do is, I'm assuming that most of the people here are electrical engineers or computer scientists, and they would appreciate a block diagram level interpretation of the nervous system. And it also helps to actually set this framework right, because that would allow us to talk about solutions, talk about how we can actually get around some of the problems caused by, in this particular case, spinal cord injury. So let me start with this. The nervous system in the human body consists of two main parts. One is the central nervous system that consists of the brain, the brain and the spinal cord. And then you have the, then you have the peripheral nervous system. Okay? Peripheral nervous systems are basically nerves that innervate all of the rest of the body. They record the state of the body from everywhere. They also can provide instructions from the brain to different parts of the body so that muscles can contract, movements can take place, and so on and so forth. Okay. So now let's, and basically how this works is when you need to make a movement or any action really, okay, the brain makes the computing. The brain is, of course, the compute power here. It does all the calculations, it just figures out and does all the analysis based on the feedback it is getting through the eyes or sense of touch or whatever it is. And then basically it makes some decisions. And then it needs to tell the muscles, for example, to do something. And how the brain communicates is it communicates through electrical signals known as action potentials. It's basically you have the action potentials or you don't have the action potentials. And when the brain has to send a whole bunch of information, it probably will send more number of action potentials than otherwise. Okay? And these action potentials travel through the spinal cord, through the peripheral nerves, to the intended locations. Okay? And that might cause muscles to twitch, contract, and movements to happen. When these things happen, of course, you record the sensory nerves would, of course, record information about the state of the body and send that information back through the nerves and the spinal cord back to the brain too. So when you have a spinal cord injury, what happens is this transmission channel is broken, and that's what I have shown here. Okay? So when the transmission channel is broken, I'm trying to put it in the electrical engineering context here really. Okay? When the transmission channel is broken, it's not that the nerves are not working. It's not that the brain is not working. It's just that the brain cannot communicate with the peripheral nerves. So the solution is somehow we can get around this breakage and make the connection directly somehow. How do we do that is part of our solution. Before I tell you how to do that, what kind of devices we use and things like that, let me tell you a little bit more about neurosystems so that what I say will become more clear. So this is a sketch of the cross-section of a nerve. Okay? And what happens is the nerve contains a lot of nerve fibers. And these nerve fibers are bundled into what is known as the fascicles. And so a single nerve can have many fascicles. Okay? And each of these fascicles can contain motor nerves that affect the movements and sensory nerves that detect changes in the state of the body and things like that and send it back to you. Okay. Now, this, this is what is known as a Utah slanted electrode array. Okay. And what it is it is a 2 millimeter, actually it's a 4 millimeter by 4 millimeter device that contains 100 different electrodes. Only the end top is actually conducting. So the rest of it is isolated, basically insulated. One other thing I want you to notice is, oh, come on. Excuse me, I did something funny. Okay, I think I'm okay now. Yeah, one other thing I want to notice is, you will see that these electrodes are shorter than these electrodes. Okay? Now, this is the same electrode array basically compared against a penny so that you can see the size. Okay? So what you do is, this is of course essentially depicting the nerve. What you do is you implant these arrays in peripheral nerves. You can also implant these arrays in the brain if you want to, but we are doing mostly peripheral nerve work. It's less invasive and it's less, it causes less problems for sure. Potential for problems is a lot less for sure. Okay? So what happens is when this is implanted, the shorter nerves would reach here and can actually sense activity in the motor nerves and send information to the sensory nerves. Okay? The taller electrodes would go deeper and can sense activities from the fascicles at the bottom in this particular example. Okay? So the idea is, because these electrodes are so close to each other, and because these electrodes reach different fascicles and different sets of nerve fibers, you can have an enormous amount of selectivity in what part of nerves, what nerve fibers you record from, what nerve fibers you stimulate for sensory information, sensory feedback. So I want to just give you an idea about the selectivity that is possible. Okay. This was actually an experiment that was done by my daughter several years ago, almost 8-9 years ago. And she was a student in one of my colleagues' lab at that time. And so what we're doing is, this was an experiment on a rat, and she had implanted an electrode array into, I believe, the sciatic nerve in the rat, okay, and was trying to find out what kind of activities, nerve activities, were created during specific movements. She tried 2 different movements. One was the plantar flexion when you actually stretch the leg out, and the other was dorsiflexion when you stretch the leg backward. Okay? So what's happening here is this. Basically, what you're doing is you're showing electrode number 14 and electrode number 21, and out here you have plotted in an overlapped manner the action potentials that were recorded from electrode 21, and out here you have plotted action potentials that were recorded from electrode 14. And what you're seeing is when dorsiflexion happens, that is when the legs were moving inward, only electrode 21 was active. Okay. Look here and here. And electrode 14 was not active at all. But when plantar flexion was happening, only electrode 14 was active. What that means is by looking at where the signals are coming from, where the activation is created, you can actually tell what kind of movement is happening. All right? And this is very, very important. And it's this kind of selectivity that is allowing us to create movements artificially in paralyzed persons. Okay? Now, the selectivity is a lot more than that. In fact, she did experiments where she was poking on different parts of the body a little bit at a time, tiny pokes, okay, with the finger basically. And you could actually see that the electrodes, the nerve fibers that were activated were different for different locations. So enormous amount of selectivity, and that helps us tremendously. So let me talk to you now about functional neuromuscular stimulation. Essentially, what I want to talk about is how you can evoke movements in a paralyzed limb by applying electrical stimulus to the nerves. So the idea is this. We have implanted this electrode array. Again, ours is not the only electrode array you can have. There are several other types of electrode arrays that people have worked with and created, and any of them will work. Okay, in the sense we just work with these Utah slanted electrode arrays, mostly because it was developed in our labs. When I say our labs, I didn't do it. Some of my colleagues did. Okay, and we have found them to be very, very useful. Okay? So what happens is we use constant voltage pulses actually to stimulate the nerves. Okay? So the idea is when you apply a pulse like this, we usually apply a biphasic pulse. That means that we will have something that goes like this and goes like that up a little bit. Okay? When a pulse is applied, a twitch force is evoked in the muscle. This is actually the force in response to a pulse like this. Okay? If the pulse is wider, the twitch is stronger. Okay, you can see that the height was higher here, right? Now, if you apply another pulse in addition to that, you will get a different twitch in response to that, and at a location at a time that correspond to when the second pulse was initiated. Now, if you apply that pulse a little later instead of where I applied earlier, the twitch will happen a little earlier. What that means that the overall shape of the force profile is going to be different. So the idea is this. You can apply, if you can figure out what kind of pulse sequence at what times and what widths you provide, you may be able to evoke muscle forces that follow a desired profile or a trajectory. That's how we do things. And that's the whole idea. Okay. Now, so the question is, how do we design the stimulation behavior, stimulation paradigm? And what I mean by that is I need to know the times, I need to know the pulse widths. Okay. By the way, this talk is a very broad talk. I'm going to give you only a 10,000-foot view of the whole field. I'm not going to use a lot of equations. This is only one of 2 slides which has equations, and I'm not going to spend too much time talking about it either. The first thing we tried, I'm a signal processing person. I said, I know adaptive filters. Why don't we try gradient descent algorithms? Okay. And we actually created a gradient descent algorithm. And that talked about the amplitudes of the twitches, or correspondingly the pulse widths, and the timing of the pulses, okay, using gradient search. And it worked reasonably well. But later on, we ended up using proportional control. We mostly use what's known as a PIV control, proportional, integral, and velocity-based control. And there's a 2016 paper that explains all this in detail, but I will just show you some results. So essentially, each of these curves has 2 plots. Each of these plots have 2 curves in it, one in orange and one in blue. The orange is the desired force profile, and the blue is what was evoked in our experiments. These experiments were done on a cat. Basically, what we were doing was anesthetizing the cat to simulate paralysis. So we don't really do anything bad to the cat, but the cat, of course, had an implanted electrode in its leg. Okay, and the difference between this plot and this plot is just that this one is zoomed a little bit more so that you can see the jitter in the evoked force. Okay. And essentially, this is just a slightly different. This was a pure sinusoid. This was a little bit more complicated signal. So what you're seeing here is that our approach does evoke muscle movements that closely match what we want to do, what we want the cat to do, but using external stimulus. Okay. One thing I have not done here is talk about how does the cat know what movements to make. In this particular experiment, we decided for the cat what movements to make. But the second half of the talk is all about how do you figure that out. Okay. So I want to actually show you a video of an experiment we did. You can see the cat's leg in this particular figure. And what we're trying to do is the cat is anesthetized, and we take good care of the cat. Don't worry too much about that part. Okay. And basically, there is a plate out here. And what we do is we would push with the plate mechanically the leg so that it's closed initially. And then from that point onwards, I will electrically stimulate the nerves, peripheral nerves in the leg, and make the cat push the plate backward, hold it there for a few seconds, and bring the leg back. Okay, that's what I'm going to show. So here is the thing. Just watch carefully. So this is mechanical movement. Now I'm going to push back electrically. Everything is electrical now. You can see the movements are relatively smooth, but you can also see some unwanted movements here. In here, right? All right. So the idea is we are in a position now to evoke reasonably smooth movements. I will not call it natural yet, but it's getting close. Okay, and so that's where we are in this particular business. Okay, okay. So I want to quickly show you a couple more things, just to show you that this controller that I talked about is fairly robust. So what I did there was actually I moved the leg to a particular position. What if I want to move it to different positions? Will the behavior be the same? Well, what we have done is we have done different step movements and are showing that except for the very large steps, the movement behavior is about the same, which is nice. What if the load changes? Again, except for very large loads, things look pretty good. What if there is a disturbance at times? Well, it looks like our system can actually get rid of the effects of disturbance very quickly. Okay? And how about stability over time? So here are two experiments. One was done right after the implant was done, and that's this one. This one, I think you can see. And the other one was done 19 days later, using the same set of electrodes and so on and so forth. And you're getting almost the same behavior, which is wonderful because you need that kind of stability in order to get to apply these things, to use this thing in practice. One last thing about functional electrical stimulation. How do you compare? How does this external control of the leg compare with human control? So what we had is we had 3 different people do the same experiment the cat did. Okay? Except for pushing with the leg, these people were pushing with the fingers. Okay? And what you're finding is we have 3 different kinds of movements. One was a ramp, one was a step, and the other was this a little bit more complex shape. Okay? Oops. So what you're finding is this. The behavior of the cat is shown here and here. What you're seeing is it's a little slower than the human beings, but it really is not that bad. If it's a choice between paralyzed and not being able to move versus moving a little slower, I will actually be happy with this thing. At least that's my thought. Okay? So that's the first part of my talk. Now what I want to do is to spend some time talking about movement intent decoding or interpretation of movement from bioelectrical signals. In the previous part, in the first half, I was talking only about animal experiment. In this part, we have done a lot of human experiments. Okay, so this is actually one of our subjects. This is one of our subjects. Okay, and I will talk about all these things in more detail soon, or some details soon. The idea of this block diagram is this. It shows you each block that is involved. So basically what you do is you collect data. If you're using machine learning type algorithms, you need to train the systems with the data collected. Okay. So what you do is you collect the data, you clean the signal up, extract some features that correspond to the movement, that correlate well with the movement, design a movement interpreter or a movement decoder. And if you're actually using it in practice, you collect the data, clean up the signals, extract the features, use the designed decoder to evoke movements. And before you actually send it to the controller, you may actually do some processing, for example, to remove jitter and things like that. And keep repeating that. We will talk mostly about the movement intent decoder. In fact, we will talk only about the movement intent decoder in this particular talk. So decoding neural data, the most common approach these days is to use a Kalman decoder with linear models that relate biological signals or features of biological signals to movement. We have been using, as I said earlier, primarily electromyograms, EMG signals, both surface and muscular, intramuscular EMG signals, okay, for control of prosthesis for arm amputees. Okay. In our experiments, sometimes we actually provided the human subjects with prosthesis, actual prosthesis. In some experiments, we actually used a virtual prosthesis where the human could actually see a prosthetic device on a monitor, computer monitor, and control that. Okay, and I will show you experiments involving both of these things. So let me start with a couple of videos just to show you what can be done. These results are about 2 to 3 years old, but you get a sense of these things. And this person is actually wearing a high fidelity, high degree of freedom movement prosthetic arm, but it controls only about 6 degrees of freedom. So it's not fully functional yet. And the controllers are not what I will call natural, in the sense that you will see differences in the way the prosthesis operates rather from the hand compared to the hand. And in this particular example, what we were trying to show was, or find out, was whether this person can learn how to move objects from one side to the other side, pick up objects from one side to the other side. Now, you will see that the picture is upside down here, but as soon as I start doing it, playing it, it will turn to the right way. I have no idea why it happens. This is the only way I have found I can use it. Let me see if it will work this time. Oops.
There is a freedom position control, the wrist and flexion.
So there is a little bit of awkwardness in it, but still he's able to pick up these objects, and so the hand itself and the ankle are not actually implemented here. Okay. Anyway, so you can see that he's able to do things which he couldn't do before. At least that's the main thing here. Okay, main message here.
There is a freedom.
Okay. This is more a cheesy episode more than anything else. This is our subject, and we have permission to show these pictures and things like that. So the first time he was fitted with the artificial arm, and these arms can all not just do the things; it can also stimulate the sensory nerve so that he can feel things. Okay, so he was very impressed with what was going on. He had been amputated for about 10-15 years, and this was the first time he could feel something in the arm. So the next time he came, he actually brought his wife so that he could touch her with that arm. Okay, and that's what's happening here. Okay? Just a feel-good story, nothing more than that. So this is another of our subjects. This subject was actually sent home with an artificial arm, and we are going to. I'm going to show you again. You will see a lot of awkward movements and things like that. But the whole point I'm trying to make is we are at a stage where these people can do activities of daily life to a reasonable extent, not perfectly naturally, not very gracefully even, but still do things. I'm just going to show things with all its faults. I will show those results.
I don't know what gesture.
So he can open the arm and.
So now it's in fist open or close.
It's a little slow process here, and he has to think through this thing. But it's all controlled by his thoughts.
Do you have it set up for going forward or backwards?
Yeah. Oh, look, I'm in the wrong spot.
Okay, that part is not implemented, so yeah. He's able to open the fridge and pick up something.
Sometimes it works, sometimes I get stuck. Yeah. Get the silicone sleeve because we have some tack. Yeah, grab some out of the fridge. Like that carrot cake up there. I like that for you, you know that? I thought you were joking. Oh, no, I wasn't. I know you love sweets.
So he's able to grab it.
But again, I'm doing a lot of movement. I'll back up so I'm having to dip my shoulder and maneuver because I don't have any of this. And I'm not going to stick my whole body in the fridge to make sure my wrist is in the right position. Right. So I go put it back down. This is as good as it's going to get because we know that's how I picked it up. Drop it. Right.
Okay. So that's, again, this was about 2 years ago also. So we have done a little bit better. We can do a little bit better than that right now. And I will show you what I want to do is how can you do better than what you are seeing here. Okay. Now I will show you experiments done in the lab. I will talk about signal processing machine learning type algorithms that can do better. Okay. So I will talk about 3 different things in the rest of the time. I'm assuming that I have about 10 to 15 minutes left, right? So the first thing is, rather than using a linear model, why not use nonlinear models? Okay. So we are going to use neural networks, machine learning based algorithm. But it turns out that a lot of people have tried neural networks, and a lot of people have actually reported saying things like, it didn't work as well as the Kalman filters. And what I'm going to tell you is that it will work better than the Kalman filters, but you need to train this network well. If you don't train it properly, it is not going to happen. We'll talk about a shared human-machine control. Basically, if you have 2 different types of movement intent decoders. In our case, we are actually assuming that we know the goal in one decoder, and then we are actually using a Kalman decoder in the other. Can you combine them to get better results? Can you combine them to improve the behavior? It turns out you can. And then online learning or adaptive parameter update for the decoders. Okay, so we'll very briefly and very quickly talk through all these things. So I'm just going to show you results more than anything else. Okay. So here is the mean square error, normalized mean square error associated with a Kalman filter done in the lab, measured in the lab, and a multi-layer perceptron and a convolutional neural network. Obviously, you can see that the neural networks work a lot better than the Kalman filter. And that's essentially the point that we are trying to make. Okay. Again, you can see a lot. There are a lot of information in how we created this thing, including how the networks were trained. And in fact, I will talk about that for one more slide, I think. Again, you can see all those things in our Transactions of Biomedical Engineering paper of 2019. Okay. So let me just show you how this behaves. Again, remember I told you that sometimes we work with virtual prosthesis, and sometimes we work with actual prosthesis. This one was with virtual prosthesis. What I'm going to show you how the Kalman filter followed commanded movements. Here, it's commanded movements. And essentially, the idea is I want this hand to follow this using bioelectrical signals taken from the human subject. Okay, Kalman filter at the bottom, MLP at the top. And I'm going to show the top first, I think. Let me see. Yeah. So you can see that the MLP here is following the movement here reasonably closely. Okay. Okay. Again, you cannot control the little finger with completely independently, and that's what you saw there. Let me show you how the Kalman filter behaved, and you will see the improvement in performance in our results. Okay, again, same thing. See, it's not working as well. It's trying to do things, and sometimes it can do it, and sometimes it's not doing as well. So at least these results indicate that the MLP is, in this particular case, the multi-layer perceptron network is working much, much better. And that's the point I wanted to make. So now, how do you train these things? So essentially, what we are doing is we use something called data aggregation. Okay? And what it is an iterative process. And in the iterative process, what you do is every time, in every iteration, you do a training, you decode the original training data, and augment the training set with the decoded outputs also. And the idea is when you do this, you actually are expanding the movements that are available that the system is trained on. Okay. So let me just quickly, again, I don't want to give you a lot more details. The 2019 paper talks about all these things in great detail. Okay. You can read it if you're interested. But I just want to show you some results. So what happens is this is the standard backpropagation based results. The normalized mean square error was about 0.63 or something like that. Just one iteration of the data aggregation algorithm, you got down to about 0.6 or 0.7. Okay? Not only that, you got down much below the Kalman filter. Kalman filter was about 0.1. So when people report that you didn't do as well as the Kalman filter, this is what you're reporting. People haven't done the training properly. Okay, so you need to be careful. I'm not saying that Dagger or data aggregation is the only way to do it. There are many different ways you can do the training, but you need to do it well in order to actually get good performance. If you don't do it well, you will have problems. Okay? So I talked about shared controllers. I just have one slide to talk about. And what we do is we create two different types of decoders of movement interpreters, and each of them may have benefits of its own and some drawbacks of its own. And we are going to do a controller that's a linear combination of the two. Essentially, in some kind, you can look at it as a diffusion process if you are familiar with adaptive filters based on diffusion and things like that. It's essentially the same thing. Okay. So again, what I'm going to show is how a Kalman filter alone works, and how a Kalman filter that also incorporated some information in this manner, using some goal estimation process performed. Okay? First, the Kalman filter. All I was trying to do was to move the thumb, the point finger, and the middle finger, I believe. It's having a lot of trouble doing the things properly. It's trying to do the right thing. You can see that. But still, and this is actually a human being trying to do it, but having some trouble. Okay, let me just go to the shared controller. Thumb, pointer, and okay, it was actually the little finger, not the middle finger, as I said. Okay. Anyway, what you're seeing is, let me see if I can show that. What you saw is the movements took place just like that, without any problems. Okay, and that's the kind of things you can do with a little bit more complex or sophisticated signal processing machine learning algorithms. Finally, I want to talk about online learning or adaptive implementation of these decoders. Okay. Again, the idea is you start with a trained decoder, but you continue to train it or continue to learn as new data comes. But the difference between training initially and now is that you don't know what the intended movement is. Okay? So what you do is you detect the movements. Once you detect the movements, you fit a model of the movement with the data that you have. And this is the kind of, we ended up using a simply piecewise linear movement model, okay? And you have to do this for every degree of freedom in the movement. And then see what happens. This is just showing one set of results. And these results are actually obtained over a span of 150 days. Okay? So essentially, as you go to the right, you are showing results obtained 50 days, 100 days, 150 days after the initial training was done. Okay. The top is the Kalman filter without adaptation. The blue is a multi-layer perceptron network without adaptation. And the yellow is with adaptation. Again, you can see that there is some improvement. I would like to have this improvement a lot better, and we are working on that. But the concept actually works. That's essentially the point I want to make. Okay. Now, what's going on at this time in our labs and our collaborators' labs? We are working on wireless interfaces, sensory stimulation. I showed you none of those results, but we have some results that have been published already that shows that if you do sensory stimulation, you actually do better control of the system too. Okay. Now, almost all the things that we talked about here was actually controlling a prosthetic arm using muscles signals from the arm itself. If you are paralyzed in the arm, can you actually control a robotic arm with other muscles? We are looking at those kind of problems. Collaborative human-machine learning, where you actually, both the human learns how to actually do the control and the machine learns how to actually learn what the human is trying to do. And we are doing human experiments. In fact, we are just about beginning a 1-year-long phase of experiments where we are sending the human subjects back home with the artificial arm and the natural control algorithms implemented in the arm, and hoping that they will be able to use it without coming back for a whole month. Okay. We will tell you what the results are if I ever come back and talk to you again in the next couple of years. So before I close, I do want to make sure that I acknowledge our financial supporters for doing this research. Almost all my work is supported by National Science Foundation. DARPA in the United States also has been helping me as do a lot of experiments. In fact, the human experiments that I just talked about are actually supported by DARPA. And that is actually my talk, and I'm happy to take questions if you have any. I am also happy to stay back as long as needed.
Audience, if any question, then kindly write in chat box to John sir. Okay, and if any question, I will share the John sir mail ID also, so you will directly ask the question from through email. Okay, so any question, kindly write to John sir, and then Anku sir, please give the formal vote of thanks and certificate.
Okay, so are you saying that I will get emails, or is there a chat box on the system that I'm not seeing?
Sir, here right side corner one chat box is there. Otherwise, I will share your mail ID and.
Yes, please do that. I'm not seeing the chat box on my screen.
Okay, sir. Okay, sir. Sir, Anku sir, kindly give the formal vote of thanks and give the certificate.
Sure.
Sir, one question is that from Kharagpur, Professor Alok Dev, how to measure the accuracy between the method?
How to measure the accuracy between the methods? Okay, I did not talk about those questions at all in this talk. So when you're doing things in the lab, there are a lot of contrived ways in which you can do the measurements, right? So for example, we have a glove that is sensorized so that I know what the movements are, or the if I'm using a virtual arm, I can actually measure the position of the arm because I know exactly how the virtual arm is moving, right? So I know the movements, I know what the desired movements is, and sometimes what you do is you tell the patient, the subject, to follow a particular movement you see on the screen or on another hand, okay? And if you're wearing a glove in that hand, you can actually measure the movements. If you're actually showing things on the screen, you know exactly what you're trying to do. So you compare those things, okay? But really, the better way to measure these things is what happens when you actually create some metrics that measures the performance in daily activities, okay? And there are metrics that other people have created that we are using for those purposes. I can give you more information later on if you want to about. I can give you references and things like that if you're interested. Right. Does that